Hello, I want to do this short video about using the chi-square test to test whether there's a relation or no relation between two different categorical variables. In this case, we have two binary variables, a participant's sex, whether one is male or female, and alcohol use in the past 30 days, whether one did use alcohol in the past 30 days or did not use alcohol in the past 30 days. So in this case, this is a sample of male and female ninth graders in a high school. So you have your data here. You'll notice that there's 4 different cells. This is a typical cross-tabulation table. The margins include all of the totals. Like for instance, the total number of males are 784 males, 766 females. There's 199 individuals who used alcohol and 1351 who did not, and there's a total of 1550 individuals. So this total will be the sum of the 2 row totals. It'll also be the sum of the 2 column totals. Chi-square is a specific test that we use, which if you look at it, it looks a lot like the z calculation when we're trying to convert something to a standard normal distribution, but squared. So in a sense, this is just the right half of this standard normal distribution. This is what a chi-square looks like. Chi-square has a certain number of degrees of freedom, and we'll get to that in a moment. So the df stands for degrees of freedom, and the I here stands for each cell. So there's 4 cells. We'll call this one cell 1, cell 2, cell 3, cell 4. You could use a row and column terminology, which I will show you in a second in the handwritten version of this problem. The O in this formula here is the observed value for a specific cell. Like for instance, for cell 1, there's 691 individuals observed in that cell. And then we need the expected cell value, and then we square that and divide it by the expected cell value. And then we sum, so this symbol sigma represents a sum, and we sum across the cells from cell 1 to cell 4. There's 4 cells, and we'll let n equals the total number of cells, and there's 4 cells. This is a 2 by 2 table, so 2 times 2 is 4. There's 4 cells here. Okay, so we need to calculate the expected value. We have the observed value. The expectation is the same as the mean. Here, our calculation, the one that you might see in your textbook, is just the row total times the column total divided by the total. So when I say row total, you take the intersection of the 2 values. Like this cell is in the intersection of being a male and not using alcohol. So that's this cell value. So its row total is 784, and its column total is 1351, and the total is 1550. You could also calculate this as the expected value of cell I, and we can imagine this as being a binomial distribution, so where we count the number of successes. In this case, a success is falling in this cell, a failure is not falling in this cell. So in a binomial distribution, we have a series of what are called Bernoulli trials. These are trials where you have either a success or a failure outcome, and these trials are independent. So you can think of each individual will fall into one of these 4 cells independent of the other individuals. So these are independent Bernoulli trials. The expected value is the same as the mean value. The expected value for any cell would be the probability of being in that cell times n. So np, and then so p sub I, again, is the probability of being in that cell, and n is the total. So for instance, to calculate the probability of being in this cell right here, cell 1, it would be 1550 times, excuse me, to calculate the expected value of being in cell 1, it would be 1550 times the probability of being in cell 1. So we'd have to calculate that. And the equation for the probability would be, well, this is the multiplication rule. So it's I could say, what's the probability of being in this cell 1? That's the same as probability of being a male and the probability of not using alcohol. So that's because I use and, the conjunction and, that indicates multiplication. So it's the probability of this row event, which is the probability of being male, times the probability of this column event. probability of not using alcohol. Let's see. All right, so our hypothesis here, and like any type of statistical test, we will have a hypothesis. And our hypothesis here, well, we have two of them actually. We have a null and the alternative. The null hypothesis is the hypothesis we'd like to reject. In this case, that there's no relation between participant sex and alcohol use. In research, we always assume the worst case scenario first. And the alternative is that there is some sort of a relation between participant sex and alcohol use. We have to select our alpha, and this isn't a lecture about alpha, so I'm assuming that you understand what that is, but that's a probability of a false positive result or type 1 error. We select 0.05, which is a standard one. You don't have to do that, but it's a standard value. Our degrees of freedom is the row total, number of rows minus 1 times the number of columns, number 1. Again, this is not a lecture on degrees of freedom, but we'll just go ahead and calculate that as 1 times 1, because there's 2 rows and 2 columns, so 2 minus 1 is 1, times 2 columns minus 1 is 1, so it's just 1 degree of freedom. And if we go to a standard critical value table, for a chi-square table, we'll get the critical value. So I just like found one online that seemed really good. And if we look at this table, our alpha value, it has p here, but this is our alpha of 0.05, and we have 1 degree of freedom. And if you look at the intersection of those two, they intersect at a chi-square value of 3.84. So that's what our critical value is. So in order to reject the null hypothesis, we'd have to get a value that large or larger. Okay, so let's go, well, actually, let's go to the calculation itself. So I have a picture here of our situation. So we need to calculate the first expected value. I also wrote this out in terms of a different type of terminology, where each cell is represented by its row number and column number. So cell 1 would be row 1, column 1. This is in row 1 and column 1. This is in row 1 and column 2, etc. But I just wanted to write that down first. I don't even know why. I just felt like it. But that's the terminology we use at some points when we're talking about cells or matrices. So let's calculate the expected value of cell 1. So it's the row total times the column total. And if you go back to our, actually I should be able to do that here. We go back to our, where was I? Here, right? To our table. Oh, yes, maybe. There it is. I have a double screen here, so that sometimes makes things a little harder. Okay, so here's our table. Okay. So we have 784 times 1351 divided by 1550. So that's what we did here. Now, that works out to be 683.3, which I'm just rounding down to 683. That's, I mean, you don't have to. If you do this with some kind of software, you might end up getting a different answer because of the rounding. So that's one way to do it. I also mentioned that this is the expected value of being in this particular cell 1, whatever we want to call it. So we'd actually, for that, need to calculate the probability of being in this cell 1 here, right? So its probability, and as I said, we used a multiplication rule here, so it's the probability of being a male and the probability of not using alcohol. So that probability is, well, probability of being a male is 784 out of 1550, because there's 784 males out of 1550 total. So it's 784 divided by 1550. You notice whenever we use these marginal values, we ignore the cell contents within, right? And the probability of not using alcohol, 1351 individuals didn't use alcohol in the last month, divided by 1550. That's right here, 1351 divided by 1550. I multiply those, I get 0.44, right? Or there's a 44% chance of being in that cell. Okay, so, well, if I multiply 1550, that's a 1550, 1550 times 0.4408 67, I get 683, which is the same thing that we got here. So you can do this either way, and that's the only time I'm going to do it using the expected value. The rest of the time I'm using the more standard way that you'd see in your courses, your textbooks. So we do the same for cell 2 here. We multiply the row total times the column total, so we get 784 times 199 divided by 1550. That's roughly 101. And for cell E3, we do 766 times 1351 divided by 1550. Again, row total times column total divided by total, and we get 668. And finally for cell 4, we do row total times column total, 766 times 199 divided by 1550, and we get 98. Last step that we have to do is we have to plug these all into our formula. So this is actually the observed value. So this is the observed value for cell 1, which is 691 minus its expected value. We go up here and it's 683. So we get 691 minus 683. We square that and divide it by the expected value, 683. We do the same for each of the other 3 cells. So this is cell 2, cell 3, and cell 4, which is cell 4 you have the observed value is 106 minus the expected value, which is 98, right? And divided by 98. We square it and divide by 98. We get these values here and a final chi-square value. Again, this would differ if I did it with, say, one of the computer packages where I allowed for more digits after the decimal point, or decimal places. So I get 1.476. So I would compare this to our critical value of 3.84 at alpha of 0.5, and because my value is smaller than the critical value, I would fail to reject the null hypothesis. So I'd fail to reject the null hypothesis that there's no relation. So I have no evidence to say there is no relation. To say that there is a relation between participant sex and alcohol use in the past 30 days. Okay, well, I hope that helped you all. Thank you very much for watching. Bye.